Hello everyone, welcome back to Physical Geology 1403. Let's turn on this projector. Whew! I was up till 3 o'clock last night. I was here working. Yeah. Combination of college stuff and what the heck keeps falling off the ceiling? College stuff and homework stuff for my PhD. Okay. What the heck is all this garbage? I don't know. It's like stretchy stuff. It's all over my floor. Like it fell from the ceiling, but there's nothing on the ceiling that would make that odd. Okay, so let's see. Just to give you some quick updates, this is the second to last day of class. We will meet next week on Tuesday where you will receive the final lecture and the final exam review. Final exam will open. The final exam will open after our review that day and close midnight, let's say Thursday midnight. Okay, so you'll have a few days to take it. What else? I'll give you more information about the final exam next week. You should have taken exam 2 by now. If you have not, do it ASAP. Yes, if you haven't taken the lab exam, take it ASAP.
What if you use all 8 hours on it, you can't turn it in?
Huh?
What if you didn't finish it, but like you used all 8 hours?
Well, then I'm not going to let you retake it. Unless you've talked to me in a special circumstance, which some people have. Okay? So, any other questions? Comments? Interesting stories? He's talked to me. How about we let Jackson speak for himself from now on, all right? Sound good? He has a mouth. He can defend himself. He can justify himself. All right. Yes. Hold on. Yeah.
When do you have another game for like that sport that you do?
When do I have another rugby game? Like an official game? Not for a while. These days, we're lucky to get a couple practices in a week. Everyone's really busy. Usually during summer things get really busy, and then once we start moving into winter, we can actually start playing more regularly again. We don't have a game scheduled for a while. Just practices a few times a week when we can manage it. Yeah.
When will you be grading our exams?
Exam Tuesday I'll be grading on Monday. Monday's going to be my big grading pass-through. Okay?
Are there like any other assignments outside of this exam?
You're getting Lab 5 today.
And then like after lab 5, it's the final exam?
After Lab 5 should just be the final exam, yeah. Assuming that you've kept up with all of the assignments as they've been coming due. All right? Good questions. Anything else? Yeah.
I'll hold the snake.
Sure.
Well, let him marinate for you.
Let him marinate?
Yeah.
He's not a steak, brother. He's a snake. Marinated snake. All right. Other questions? Other questions? Nothing? Any cool stories? Any cool scientific stories that you may have heard about? No? All right. Should we jump in then? Oh, class movie night, Friday, 6 o'clock right here in this room. Obviously, if you're watching this in term 2, that doesn't apply to you. But yes, there will be a little bit of extra credit available. It'll be fun. We'll have a good time. Yes?
Can we bring people that are not in this class?
You can bring people that are not in this class. Know that San Andreas is PG-13. So if you are planning to bring any children, friends, or relatives or anything like that, just be aware of that.
I wanted to bring my friend, but she doesn't go to this school. So.
That's fine. No, you can bring family, friends, whatever. Make a movie night out of it. Bring snacks, bring drinks, all of that. All right. Anything else? Okay. Let's do it. Today we're talking about earthquakes and plate tectonics. Hooray! Finally. Well, it's not Die Hard time yet. We're not even at Christmas. Okay. Okay. Earthquakes. Can someone explain to me what an earthquake is?
When tectonic plates either collide or move apart from each other.
When tectonic plates either collide or move apart from each other, what does that do? Okay, so you can have volcanism as a consequence. That's true. But what is it doing?
Shaking the earth. Seismic energy.
Okay, so it's doing something with energy. Yes. Okay, there's a lot of energy at play here. Energy is the reason why they're moving in the first place. Energy is a consequence of them running into or moving away from each other. That's true. Some of that energy is manifest in volcanic eruptions, but there are other ways that that energy manifests itself as well. What happens when I drop an object? But as it falls, it picks up what? Speed. We call that acceleration. That's due to the effect of gravity on Earth, okay? Now, by the time it reaches the floor or whatever surface it impacts, it has picked up a certain amount of energy. The further it falls, the more energy it picks up until finally it impacts an object, and then what does it do? The easiest way to imagine this is if I were to tell you that I am dropping this object into water. What does it do when this object hits the water? Splashes. It makes a splash and
Slows down.
it does slow down because it is doing what?
Losing all of its energy.
It's not losing it, it's transferring it.
Yeah.
Into what? The water. And what does the water do? Yeah. I already hit record. Didn't I hit record? Now you're going to make me check. Keep your thought going.
Is your microphone working?
I already checked it, yeah. Yep, we're recording.
Water, like spreads the energy. So it's like those little waves.
What do we call those little waves in the water? Ripples, yes. Ripples are the energy being transferred from the object into the water, okay? Remember this. This is going to be important in a little bit, all right? So, earthquakes are a movement along a plane caused by the buildup of energy. These planes can be either plate boundaries or these things that we call faults. Okay, I'll teach you about all the different types of faults here today. Now, earthquakes, everyone is really scared of, really leery about. Why? Well, because they generate energy and create damage. Nobody wants their house or their business or whatever damaged by an earthquake. You don't want your windows shattered. You don't want your house to collapse. You don't want a giant crack in the earth to open and swallow you whole, right? Nobody really likes the idea of an earthquake. So let's talk about that today. It's actually very relevant to something I've got going on. I've told you all about this event I have going on the 24th. Have you guys seen the posters I put up last night around campus? I put them on every door on campus, around every door in and out of the building. If you look, then you'll see the Odessa College Energy Fair posters, okay, or Energy Day posters, okay? That's an event I'm putting on October 24th. It will be in the Wood Health Sciences building from 9 to 4. And the point is I'm bringing people from the oil industry, so a whole bunch of companies, and a bunch of seismic scientists from Lawrence Livermore National Laboratory in California, from the Department of Energy, from Texas A&M. The Texas State Seismologist is going to be there. People from the Texas Bureau of Economic Geology are going to be there. So there's going to be speakers, there's going to be panels, there's going to be a whole bunch of stuff. There's actually going to be a student-oriented panel that talks all about careers in the oil industry and in science and in policy and in all of that. And the point is to try and get everyone to recognize that we're all working together towards the same goal here. And that is nobody wants our oil field activities to make earthquakes. Nobody wants something that we're trying to do for the betterment of our civilization. to end up causing something that is negative for our civilization. We've done that too much already. We should know better. We do know better. And that's why we are trying to not do that anymore. These days, it's really easy for people to villainize the oil industry and say, oh, they don't even care what they're doing. They're going to keep drilling. And it's kind of a damn the torpedoes full speed ahead sort of thing. Who cares about the consequences? But that's not what's happening. The oil industry people are just as invested in making sure that their activities don't cause damage as we are. So this event is designed to get the public, the scientists, and the industrialists all together on the same page so that we all understand each other a little better. So please feel free to come to that. I will be offering extra credit for those of you that are in my class during that week. Okay? Those of you that are taking historical geology from me that week, or that term, because this will be in term 2, I will be offering a little extra credit for going there and then giving me a little bit of a write-up about it. Okay? Especially that student panel. That student panel should be real good. Okay? Any questions about that event or anything? No? All right. Okay, so let's talk about faults here for a second. A fault, I keep forgetting. A fault is a crack in the earth. So it's not an object. First of all, I want to point that out. A fault is not an object. It is not a thing itself. It is a crack, right? It has no substance itself, bless you. It is a line between two halves of something, okay? So when I develop these cracks in the ground, it's because stress, tectonic stress, has built up so much that the material, the rock, will actually, it can't take that stress anymore, and it cracks. But then that stress builds up again, and then again, and again, and again, and again, and this is what generates an earthquake. So we have 3 different types of faults, okay? This is our plane of our crack, of our fault surface, okay? So your first type of fault is called a normal fault. Then you have a reverse fault. Then we have a strike-slip fault, okay? Now, what makes these normal, reverse, or strike-slip? The movement that is caused by the buildup of energy along this fault plane determines what type of fault it is. So the side of my fault that is above the angle of the fault line is called a hanging wall. What do I mean by above the angle? You see the angle of my fault surface there? Below that, there's an acute angle. Above that, there's an obtuse angle, right? So above the surface of my fault is that side. That is the hanging wall. Below it is the foot wall. Now, this can get a little confusing because you may be inclined, a lot of people lean towards this, to think that hanging wall and foot wall are terms that have to do with the movement of the fault or of the energy itself. That's not the case. It has to do with orientation to the fault line, okay? So, hanging wall, foot wall. In a normal fault, the hanging wall is moving down relative to the foot wall. So we get stretching motion. This is the sort of fault you get in a place where the stress is pulling the crust apart, okay? In a reverse fault, the hanging wall is moving up relative to the foot wall. This is what you get in a compressional stress situation, okay? Where the crust is getting shoved closer together. What about a strike-slip fault? In a strike-slip fault, there is no motion up or down, only side to side, okay? And this happens when you have different forces torquing it at the surface level in different directions, forward and backward, not up or down, okay? So these are the 3 types of faults that we can get. And along each one of these surfaces, energy will build and build and build until it releases. Now, once that energy releases, do you think that's it?
Is that it? One earthquake and then it's one and done? No, why not?
Because all the energy is still there.
Well, the energy's been released in the earthquake. Yes, exactly. Whatever forces caused that earthquake in the first place are going to keep coming back. It's tectonic. It doesn't just disappear. Yeah, don't let him get in anything that he can't get out of or that we can't easily remove him from. Okay? So that's what's happening in an earthquake. Let's talk a little bit about the components of an earthquake. When you watch a news report about an earthquake, they will often use terminology like epicenter, where the epicenter of the earthquake was 20 miles north of Gardendale or whatever, right? What does that mean? That is the point on the surface where the earthquake waves first manifested. Okay, that's useful geographically speaking, and that doesn't give us a whole lot of information as geologists. What we care about a little bit more is the focus. The focus is the place underground where that motion first occurred. It's directly underneath the epicenter, just at a certain depth. So while it may have been 20 miles north of Gardendale, it may have also been 17 kilometers deep, right? It means a little bit more to us. So our focus is going to be underground, and when that motion first occurs, when that fault first slips, that energy is going to spread out. And how is it going to spread out? In what manner is that energy going to spread out? In what shape, in what format? Excuse me. What do we think?
In all different directions.
In all directions? Yeah, it's going to spread out as a sphere of energy underground. When I do this, here, listen. When I do this, did you see that sphere of noise spread outward? No, you did not, because it's spreading through air, right? You can't see that energy moving through the air, but underground, that's a lot thicker. That energy is a little more manifest. It spreads out as a sphere of energy. It goes deeper, it goes to the sides, it goes up. Now, if I had a flat surface, like a sheet of paper, and I threw a ball at it, there's a sphere that's going to interact with a surface. Only one point at the very top of that ball is going to interact with that paper first, before the rest of the paper, or before the rest of the ball rips through the paper, right? That one point at the top of the sphere is where your epicenter is. Imagine a giant ball that's moving up towards the surface. That's your epicenter, where that ball first contacts the surface like that. So from your epicenter on the surface, a two-dimensional plane, it's going to appear as rings of energy, waves, that are translating across the surface. But underground, it's actually a sphere of energy that is expanding outward. Okay? You following that 3D to 2D relationship there? Three-dimensional under the surface, but once you hit that surface, this two-dimensional surface, it becomes a circle. A sphere in 2D is a circle, right? Right? Good. Okay. So you've got your focus, you've got your epicenter, and you've got your seismic waves. Okay? So what's causing... Come on now. Not this early. Don't crash out on me. There we go. Woo! Huh? All right, so what causes an earthquake? It's a buildup of stress, like I was just mentioning. All right, so this is what we call elastic stress. You all know this concept from rubber bands. What happens when I pull on a rubber band?
It stretches.
It stretches, but what you're doing is you're adding energy to it. It is building up the energy inside of that material. And eventually what happens?
It's not
Yeah, it snaps. Either in one of two ways. Either your fingers, the friction of your fingers, cannot fight the elastic energy of that rubber band and it slips through your fingers and hits your other fingers, and ouchie. Or the material itself of the rubber band snaps because of the buildup of elastic energy. Okay, either one of those circumstances works here. That's the same thing that happens underground with an earthquake. The elastic energy, it builds, it builds, it builds, it builds, it builds on both sides until finally the surface slips and that energy is released and you get earthquake waves. To imagine this, everyone put your hands together like this. Now push them together as hard as you can. Now try and slide your right hand out in front. Push them together as hard as you can. And now try and, yeah, you see that? It took a lot of energy, but eventually it did. And then that built up energy released along that surface between your two hands. Now, imagine if you did that while your hands were wet. Would it be harder or easier? Easier. Way easier. Yeah, exactly. And this is where things like water and other fluids that get introduced to faults can be a problem. Okay, this is the sort of stuff that we're studying in the oil industry to make sure that none of the stuff we put underground or none of the stuff we're in the process of removing from the ground can be introduced into fault systems and cause earthquakes to slip early. Okay? Okay, so you get that buildup of heat, of energy, build up. Friction is overcome by the amount of energy. Energy is released as waves. We make an earthquake. Okay, now you've got your actual main event, your earthquake, but you can have smaller events that lead up to it and smaller events afterward. We call anything that happens before the main event earthquake a foreshock. And anything that happens afterward, an aftershock. I know, real original names, right? Real hard to remember. So, this is what's called a seismograph reading. I'll show you more about these in a little bit. But basically what happens is we have our main event earthquake right here. And these things have added up to it. Okay? This just happened. But before that, we've had these things. These are foreshock readings. These are little earthquakes that have happened prior to the main earthquake event. And then all of a sudden we had this big guy right there. Okay? I know, right? This one is clearly bigger than those.
How big is it?
And this one, it doesn't have the measurements on it, so I can't tell, but it's still big. The thing with a seismograph is the amplitude of these waves is equivalent to the amplitude of the earthquake. I'll tell you more about why that is the case when I explain how seismometers work. But if I have, say, a 5.0, we might think, oh my goodness, we just had a 5.0 earthquake. But if an hour later we get a 6.3, we know that 5.0 was just a foreshock. Okay? And that's how we refer to it after that point. All right, I already explained how faults work. Just a little bit of a reminder. Normal fault, hanging wall moving down relative to footwall. Reverse fault, hanging wall moving up relative to footwall. Strike slip fault, they are moving sideways. Okay? There is a very famous strike slip fault in our nation you've probably heard of, and which we will be watching a movie about tomorrow called San Andreas. Yeah, the San Andreas fault is a strike slip fault. It's going to be very important to remember when you're watching the movie. Huh? What?
He said GTA.
GTA? Oh, because there's a GTA game called San Andreas? Yeah.
There's actually an earthquake that happens and it's created in direct mode and they make it into reality.
In the game?
They make the beach go all the way into the city and it goes into all the houses and everything and it affects the city.
Oh, like the water?
Yeah.
They make a tsunami?
The characters in there are trying to run away from the city and survive with their family.
That'll be something we talk about tomorrow, believe me. Okay, so San Andreas Fault, I have a picture of it right here. It is a strike slip, which means is there any upwards movement or downwards movement? No, only that side-to-side movement. Okay? which is actually the reason why it is prone to so many earthquakes. You tend to have more earthquakes in that side-to-side movement because the energy builds up and releases a little bit faster because it's not fighting gravity either way as you do with a reverse and a normal fault. Okay, so how do we study these earthquakes? We use devices called seismometers. Now, and they generate seismographs. The study of earthquakes is called seismology. You get the picture. Anything that is a seismo has to do with earthquakes, okay? Or the study of waves interacting with earth materials. So how does a seismograph work? Well, I've got a dummy version right here. And I have an actual seismograph that I'm going to be getting here pretty soon, I hope. I was hoping to have it in time for this lesson, but it didn't happen. My partnership with the laboratory for this event on the 24th came with a little bit of funding. I'm using that funding to get an actual seismograph that I'm going to install here at Odessa College to measure our local earthquakes. But what happens here is, let me tilt it a little bit. Okay. Move that a little. Okay. So, when my Earth's surface is shaking, this arm is going to swing back and forth as the ground underneath of it shakes. And as it swings back and forth, and this barrel is constantly rotating, it's going to draw waves on this paper. The amplitude of the waves on this paper is directly equivalent to the amplitude of the waves from the earthquake. Okay? That's how we measure how powerful an earthquake is using a seismometer. We have stuff that works just like that, but is more digital now. That's the kind I'm going to be getting. So it's not as big or clunky as this. It doesn't require a whole thing with an arm and everything. It has a little micro reader that does it instead, but this is how a traditional seismograph would work. So we have these things set up all over the world because guess what? Earthquakes happen everywhere. Okay? There is no one location where an earthquake will occur, and therefore we need to know where they are. How do we use seismographs? I'll explain that more in a minute. Yeah?
So if there is an earthquake, would that go off?
That right there, the one I just had, if I had it set up. I actually built that one so that I could hook it up to a drill. I have the tube that has that roll of paper on it. I attached a drill bit to, so I just need to put a drill on that end and then tape the drill trigger closed so that it's active at a certain RPM. And then that barrel will keep rotating and feeding the paper through it. And if there ever was an earthquake, yes, that arm would swing back and forth and do it. Now, we don't get earthquakes that often around here, so it doesn't make sense to have that going all the time. So I just use it for a demonstration, right? I've got that real seismograph coming in a little bit, and we'll use it for the actual studies of earthquakes in the area. All right. So, but this wasn't the first device, by the way, that has been used to study earthquakes. 3,000 years ago, the Chinese built this device, which is essentially a giant metal egg. Where's my black pen? There it is. A giant metal egg with a suspended weight in the middle. Okay? This weight is attached by arms to these dragon heads, and suspended in each dragon head is a little ball. Just barely there, sitting there between the teeth of the dragon. Whenever there was an earthquake, the waves would encounter this egg with the free... Gentlemen, come on. Okay? The waves would encounter this object, and because of the direction that the waves are coming from, it would push the weight in that direction and cause the ball to fall out of the dragon's mouth and into the mouth of usually a frog or a fish or something statue underneath of it. And it'd go clunk, and it was someone's job to monitor this thing all the time. They go and they see, oh my goodness, this ball fell out, which means that wave came from that direction. Emperor, we should send people out that way to make sure that our people are all right. Okay? And our minds are still open and all of that. Okay? So this was actually the first device that we know of that was specifically meant to evaluate some data about an earthquake. namely the direction from which the waves came.
So they weren't trying to measure how, like,
No, there was not really a way to measure how powerful they were, but the direction that the waves came from is what this was meant for.
so what if it came like right from underneath them?
Then they have bigger problems than a ball dropping out of a dragon's mouth. Right? You don't need a dragon to tell you that there was an earthquake under your feet. Okay. So let's talk about the different types of earthquake waves. Yes, there are different types of waves, and I happen to have another device here to help teach that. You all know me, I prefer being hands-on when I can help it. All right. The first type of waves are surface waves. These are the ones that get to our two-dimensional plane of the surface of the Earth. I'm treating it as a two-dimensional plane for the purposes of the physics here, okay? When all of that force goes to a two-dimensional surface, it's going to cause movement on that two-dimensional surface. Remember that object, let's say a rock that I dropped in the water? What happened? What was the effect? Yeah, it spreads outward in a circle, right? Manifests by ripples. Ripples are displaced water because of the energy that has been transferred to it by the object I dropped into it. So imagine a substantial amount of energy making its way from underground to the surface. Where the ripple on the pool surface happens, where the pool interacts with the atmosphere. In this case, the ripples happen where the surface of the Earth interacts with the atmosphere. And so you get that movement on the Earth's surface. Those surface waves are what make all the damage to our infrastructure. Why? Because we live on the surface, right? This is where we are. Right? Okay. So those are surface waves. Now let's talk about body waves. There are two types of body waves. All right. There are two types of body waves, primary waves and secondary waves. A primary wave is one that pushes and pulls. A secondary wave shakes at right angles. What do I mean by this? Well, that's why I built this object to help show you this. What do I have here? What's this material? What is this object? It's a slinky, also known as a spring. Okay? It's a very loose spring. I'm going to provide some energy to this spring in a direction, that way. I'm just going to push it a little. I'm not going to push it all the way to the end. Watch what happens to this material. Can you guys see it past the computer screen? Should I tilt it down a little? How's that? See it better? All right. Watch what happens to this spring as I provide it a little bit of energy in a certain direction. Am I taking this point all the way down there? I'm not doing this. I'm giving it a little bit of energy in a direction. And what's the material doing? Yes. Do you see that a little bit of the spring that is compressed that's traveling all the way down? That, my friends, is a primary wave. This is a push and pull. This is how primary waves travel through rock. Compression that travels through the material. Just like this. That's your first wave. That is a primary wave. It can only go through solids. Well, no, that's true. Not true. It can go through solids, liquids, and gases. Secondary waves can only go through solids. A secondary wave is movement at right angles to the direction, or to the application of energy, I should say. Okay? Huh? It is long. It's long so that you can see the demonstration. If my camera would follow me. Hey, over here. Come on. Right here. What are you doing, you dork? Right here. All right, hold on. Let me pull the camera up here and see what's going on. It might have zoomed in on me. Right here. What is your deal? Camera's not behaving today. There we go. Finally. Better be careful, camera. Better watch yourself. I know where you live. Okay. All right, I know. I should be kinder. Okay, so now I'm going to provide a little bit of energy the same way, that direction. Watch how this material deforms, okay? How is it moving?
Wobbly.
Okay, wobbly isn't really a description of movement.
It's making waves.
Yes, it's making waves through the material. And in what direction are the waves going?
The same thing that you did. Like,
No, they're traveling that way, but the material is deforming
down.
up and down 90 degrees, perpendicular to the direction of the energy I gave it. That is a secondary wave. Okay? That is how secondary waves move. Secondary waves can only go through solids because you can't move liquids and gases at 90 degrees to the direction of any energy you put in them. Okay? Water and oil and natural gas and stuff, they don't really work like that. So, turns out this is a very useful thing to know because we can artificially generate secondary waves, pass them through the ground, and that can tell us where there is water and oil and natural gas. Wherever those waves don't go through a layer of rock, that layer of rock has some liquid or gas in it underground. Good to know. Okay? Any questions about waves? Earthquake waves? Yeah.
So is that like kind of like a nod to like the groundwater lectures? How you said that people can make money or like find water?
Yeah, that's one of the tools that is useful to know how to find water with. Yes. Yes. Okay. Let's talk about how we find earthquakes using our tools that we have. What's the tool that we have to analyze earthquakes again? What's it called? A seismograph is what it makes. The device is called a seismometer. Remember, a something meter is a tool. A graph is the product of a tool. Okay? Like a graphing calculator, right? Have any of you ever used one of those?
Yes, I have.
I use them all the time.
Graphing calculator is a tool. The graph that it produces is the product. Yeah. Huh? You use them in your math class? Great. Okay. Okay. So here I have 3 pieces of data. One from Nagpur, India, one from Darwin, Australia, and one from Paris, France. Okay? I want you guys to look at that, chew it over for a minute, tell me which one you think was closest to the earthquake. Do you suppose earthquakes stay constant over time and distance, or do you suppose they dissipate energy?
I think it's C because the waves are smaller, so there's not as much being able to.
Okay, so we have an argument for C because the waves are smaller. Energy dissipates over distance, right? A simple way to explain this is if I was standing here, Autumn was sitting right there, but Anik was all the way on the other side of campus, and I said something at this voice level, you'd be able to hear me and you wouldn't. Why? Because my sound waves are dissipating over distance through the atmosphere. Same thing is true with seismic waves. They dissipate over distance, they become less powerful, harder to read. So based off of that information, which one of these is closest to the earthquake? The Indian seismometer. Then what? The Australian. All right, sorry about that, friends. I ran out of disk space on my computer and I had to delete some old videos. All right, we are back. Where did I leave off? Oh, right. We just met Aaliyah. Aaliyah is in this circle. Where do you want to be? Where is the circle? Africa? Okay, Aaliyah is standing in Africa. That's convenient. It also starts with an A. Okay, Aaliyah is standing in Africa. She hears a noise. That noise is coming from a certain direction. But that's not really helpful if she wants to know where that noise is coming from, right? Because it could be anywhere in that whole half of her perceived world. Assuming she's facing the direction she heard that noise, it's not coming from behind her. She turned to face the direction it came from. It could be anywhere in this half of her perceived world, right? One data point, not sufficient to figure out what made that noise. What do we need? I worked with this guy from India at the gold mine in Nevada, and he was famous for saying one thing all the time. We need more data. More data. Collect more data, Josh. Right? You cannot make an observation without more data, Josh.
What's his last name? Singh?
I'm not going to tell you his name. I'm not going to put this on YouTube and talk about someone with their name. Okay? But that was what he would use all the time. We need more data here. Okay? So this is, let's see. Gavin, you're the furthest away from her, I think. Okay? Gavin over here. Okay, Gavin, where are you sitting? Norway. Nice. Norway, Africa, just so we don't lose track. Okay. You also heard that noise. Man, what a loud noise that must have been. But from your perspective, it came from that direction. Has this helped? Well, why? How? How has this helped?
Because now we know that it has to be, it can't be up or left of Aaliyah.
Yeah. To Gavin's perspective, half of his perceived world could have generated the noise, but together, Aaliyah and Gavin have narrowed it down to about 25% of the perceived world. What do we need?
Someone on that side.
More data. Yes, we need more data, right? Okay. We need more data. Okay, so here. This is Chris. She's between you two. Okay? Chris, where are you? Germany. Oh, that's not that far from Norway.
Australia. Actually, no. Antarctica.
Where do you want to be? Australia sound good? Yeah? All right. Wish I could be in Australia right now. All right. Australia. Here we go. Chris also heard that noise from that direction. What does this do, my friends? It narrows it down to a triangle specifically. That noise must have come from somewhere within that triangle that all three of you perceived the noise coming from. Much smaller area. Am I right? Of course I'm right. I mean, come on. Right? We call this a certain thing. Any guess what we call this? No, this process. This process.
Narrowing down?
I mean, that's what we've done, but what is the name for this process? This is called triangulation.
Oh, I could have guessed that. I was close. I picked triangle.
Now, how do we use this for earthquakes? Well, let's suppose we have 3 points of data, which, by the way, for triangulation, you need 3 points at least, right? More is better, at least 3, hence the name triangulation. Okay? We have 3 points of data here. We know through various studies and researches that triangulation for an earthquake, the calculation for the speed of which an earthquake can travel is S time, so the time for the S wave, right? Minus the P time, the time for the primary wave, or the secondary wave minus primary wave, okay? Times 8 kilometers per second. I'm not going to make you do the math here. I'm just giving you this to show you that we know it, okay? S time minus P time times 8 kilometers per second, which is about the average speed at which these waves move underground, okay? So we have our first P wave right here, our first S wave right here. P wave, S wave, P wave, S wave. Notice that as we get further from the source of the earthquake, the P wave and the S wave get further apart from each other. That's going to change the number here and change the distance from that seismograph or that seismometer to the origin of the earthquake. That distance does not give us a direction, only a distance. So for Nagpur, India, we do this calculation. Here's the seismograph, okay? We find that the number that gets spat out is, it's always so hard to read on that screen, 3,400 kilometers. But again, that does not tell us a direction, only a distance. So anywhere along this radius of 3,400 kilometers from Nagpur, India, that earthquake could have come from. That's a lot of points. What do we need? More data. Okay, so. Am I either? No, so I'm not good at it. Okay, so now we go to the Darwin, Australia one, which is the next strongest. We put in that calculation. That gives us, I believe this is 4,800 kilometers. So anywhere along this circle, this radius, that earthquake could have occurred. Now this is good. With 2 data points, this gives us only 2 possible locations for the earthquake. Here and here. We've narrowed it down to 2 possibilities. What do we need? More data. With that 3rd data point from Paris, France, we have a 3rd radius. And where all 3 of those meet up, that is where our earthquake happened. Right there. This is how triangulation works for an earthquake. This is why 20 minutes after an earthquake happens anywhere in the world, I get an email telling me exactly where it happened. Okay?
Why 20 minutes?
Well, you have to take into account the time for the data to reach the data centers to share them with each other, because there's not one data center this all goes to. All nations have multiple. So they all have to go to a central source. It all has to be triangulated. It has to get sent out. And then there's a speed at which emails are sent. Okay, they're auto-generated, and then they're sent to people. And then the amount of time it takes for it to show up in my inbox.
How many do you get?
I usually get 4 or 5 a day. I have it set to not tell me about earthquakes that are smaller than 5.5s.
What's the biggest one you've seen?
We'll talk about the size of earthquakes here in a minute, actually. That's the next subject. But are there any questions about triangulating earthquakes? Okay. So how exactly do we measure how bad an earthquake is? Well, there's this thing called the Mercalli scale. The Mercalli scale goes 1 through 12 and is based entirely upon the damage that is dealt to the area impacted by the earthquake. So if there is, a few things shook, but most people didn't really notice it that much, it might be a Mercalli 1. But if there's total devastation, we would call that a Mercalli 12. This is useful in some ways and not useful in others. Why? Why would this not be useful for science, let's say?
It could be inaccurate.
Why? Juliet, any ideas? Why a scale based on damage to a city would not be good for scientific purposes?
It could be different in different places.
Huh. Bingo. See, you're always so timid about answering questions, but you get them right. Okay? That's exactly correct. It could be different in different places. Let's say I get the same earthquake, okay? Let's say that I get an earthquake in the middle of the African Serengeti. How much damage is there going to be? Very little. I call that a Mercalli 1. Why? If the tree falls in the woods and no one's around to hear it, does it matter? No, not really. Are the animals going to register it with the United Nations as a Richter 12 or as a Mercalli 12? No, they're not. But if that same earthquake happens in New York City and knocks over skyscrapers, what would we call that? A Mercalli 12. And this, my friends, is the reason why, just like Julia said, the Mercalli scale is not good for science. It's relative based on whoever built something there first. Not good as a scientific baseline. Great for organizations like the American Red Cross, the Helping Hands, the United Nations, and anyone else who's interested in helping people recover from catastrophes. You tell them, we just had a Mercalli 11 event in Saudi Arabia or whatever, and instantly everyone goes, oh man, that's a bad one. We better act on that immediately. They know they'll need this and this and this and this, right? That gives them the relevant information they need. Not so for a scientist. Okay? What we use instead is called the Richter scale. The Richter scale goes 1 through 10. It is logarithmic. Do you know what that means? No. It goes number by number. It doesn't double. It does a triple. It doesn't quadruple. It goes by factors of 10. Every step upward is an increase in a factor of 10. A Richter 2 is 10 times more amplitude, not power or energy, 10 times the amplitude of a Richter 1. A Richter 3 is 10 times the amplitude of a Richter 2, 100 times the amplitude of a Richter 1. A Richter 4 is 10 times the amplitude of a Richter 3, 100 times the amplitude of a Richter 2, 1,000 times the amplitude of a Richter 1, so on and so forth. Logarithmic. Now, you could translate an increase in amplitude to an increase in energy. It roughly comes down to about a 32 times increase every time you step upward. So a Richter 2 has 10 times the amplitude, but 32 times the energy of a Richter 1. Okay? Richter 1s, we would never even feel. Richter 2s, never even feel it. Richter 3s, if you're very, very sensitive to the movements of the ground, you might, or in a very tall building. Richter 4s, yes, we feel those. Richter 5s, we feel those and they can cause some damage. Richter 6, now we're having real problems. Richter 7, catastrophe. Richter 8, devastation. Richter 9, your city's gone. Okay? Richter 10 has never occurred. There is no naturally occurring rocky material that we can calculate as being able to hold that kind of energy before it releases it. I have some energy comparisons here, by the way. So the largest earthquake in recent history in the United States was in Alaska in 1964. It was a 9.2. Then there was one in Chile in 1960 that was a 9.7. We had one in 2004 in Indonesia. It was a 9.4, I want to say. Okay. Absolutely devastating scenarios. Absolutely destroyed cities. Hundreds of thousands of people dead for these things. Okay. Now, the largest volcanic eruption ever to occur that we know of is the Krakatoa eruption. That had the energy equivalent of an 8.5 earthquake. The world's largest nuclear weapon, which I told you about early on in the class, the Tsar Bomba, was an 8.1 worth of energy. Yeah, you may. A Richter 10 is equivalent to 50, what is that? Let's see, 100, 1,000, million, billion, trillion, 50 trillion kilograms of TNT high explosive. That's how much energy Richter 10 would have. A Richter 9, 1.8 trillion. You have 50 trillion kilograms of TNT in your basement? Well, now you know how to generate a 10.0 earthquake.
So what happens if the 10.0 earthquake was with the wall? Like, what does that happen?
The world would not split in half. No. No. It would level any and every civilization tree, possibly tumble a few mountains, set off some volcanoes.
All across the world?
Potentially. There was an 8.8 earthquake in Russia last month. that set off a powerful volcano along that peninsula. It's still going, as far as I'm aware. Yeah. Not a whole lot of people live over there, but some people were definitely affected and needed to be evacuated. That's why there was a tsunami warning across the Pacific early on in September. Okay. So, why do we use the Richter scale? Because this is relevant no matter who lives where. We can measure this stuff and use it for scientific data, no matter what. Are those big playing cards? Nice. I was like, are those tarot cards at first? I was like, no, okay. No. All right. All right. So where do earthquakes happen? Well, it turns out 95% of all earthquakes in the world happen along this boundary. Do you remember what we call this?
San Andreas Fault.
No, San Andreas Fault is right there. This whole thing. It's the Pacific Ring of Fire, which happens to also coincide with the Circum-Pacific Mountain Belt. Why? All the same causes. Tectonics. Okay? Very tectonically active. Most of the rest of the earthquakes happen in the Alpine Himalayan mountain belt right there. Why are earthquakes tied so closely with mountains?
Because of the tectonic plates that form the mountains.
Right, exactly. The forces causing the mountains to form are also generating the energy for the earthquakes. Okay. So let's talk about some of the ways that earthquakes can be destructive. Seismic waves, for example. Seismic waves are going to shake things at the surface. Okay? As they shake things at the surface, don't grip them too tight. Yeah? As they shake things on the surface, they are going to cause things to tumble over. They're going to cause stuff to break. Think about the sort of stuff that we have here at the surface that we really don't want to break. Buildings, for example, don't want that. Turns out that the older wooden framed houses survive earthquakes a lot better than metal, glass, and stone houses do. Why? What?
Because it conducts energy.
Yeah, they're just able to move.
Wood is flexible. It can bend. Stone, glass, metal, famously not bendy. Okay? Wood, bendy, flexible. This building would collapse 0 seconds flat with a large enough earthquake. My house that has wood framing would last a little longer. We're in a more powerful quake. Okay? Yeah. Oh yeah, this one would go down pretty quick. Yeah. Yeah. Sorry. This building is made entirely out of glass and steel, which is great for looking good, but not great for an earthquake. Okay? So, stuff on the ground is moving. Whatever cannot bend or flow with that movement is going to break. Okay? Law of physics. All right, then there's this thing called liquefaction. Turns out that when you shake sediment enough, the water table actually rises up to the surface, and what once was solid ground turns into mud as that water from deep underground mixes in with the sediment that's moving. Dirt streets become mud ponds. If you don't believe me, just ask a guy that owned this car. During the earthquake, this dirt street turned into mud. When the earthquake stopped, it instantly re-solidified back into a dirt street. And now his car is stuck in the road. Well, you have to either dig around it or pull it up with a crane. This happens to buildings. You can look up pictures online of apartment buildings where the bottom 2 stories have sunk into the ground. This is called liquefaction. What if? It happens. It absolutely happens. Yeah, liquefaction, one of the dangers of earthquakes. Just be chilling.
Or I could like break through the roof and like have a skylight.
Jackson has all the answers, y'all.
Yeah, let's jump out the window underground.
Okay. Oh, come on. Okay, here we go. All right. Then we've got ground failure. So this includes things like landslides. Why? Remember what we learned about landslides? It relies on the angle of repose, right? If you're doing an earthquake, if there's an earthquake, your angle of repose is going back and forth. Stuff is going to fall off that slope until it reaches its new angle of repose, right? Yeah, sure. Then you've got subsidence, which is when your ground compresses. If there's, say, a cave system underground and you get an earthquake, the ceiling of that cave could collapse and causing the surface above it to form a sinkhole. Okay? Then there's stuff like fires. My goodness, friends, do you know how many gas lines and power lines run through even the smallest cities? A lot. You crack a gas line and then break a power line and introduce those two things together, what do you get? Foom. Yes, you get fire. This happened in San Francisco during a massive earthquake that happened there, which was, I have that date right here, San Francisco earthquake, 1906. In the San Francisco earthquake in 1906, there was a fire in the city after the earthquake, and they decided to try and control that fire. They would do a controlled burn around it. Do you know what a controlled burn is? Yes, this is actually a tactic that they use when they're fighting wildfires out in prairies or forests. They will actually selectively burn a strip of wilderness in a ring around the fire that is out of control, so that when the out of control fire reaches that pre-burned strip, it will have nothing to burn and it will die out right there, and you save the rest of the wilderness. You are choosing to sacrifice a strip of wilderness to save the rest. They decided to try and do that in San Francisco, and they lost control of their controlled burn and ended up burning more of the city to the ground. Right? But fire is a huge possibility when it comes to earthquakes because of the sheer number of flammable things. Think about all the toxic waste and crap that would escape from like an asphalt factory or anything else that we have in our communities, right? And then there are tsunamis. Is this video going to play? I doubt it. Okay. So instead of worrying about that video, I'll just draw it for you. Or I'll just show you with my hands. Actually, I can just show you with my hands. I have two plates. One is subducting under the other. As it does so, it is generating friction on the bottom surface of the overriding plate, pulling the tip of that plate down with it, ever so slightly. That's what makes a trench. Okay? As it's pulling the tip of that plate down, the stress is going to build and build and build and build until it rebounds upward. Boom. Like that. What happens to the water above it?
The energy transfers through the water and causes a huge ripple.
Yeah, it displaces upward and essentially makes a big ripple. Right. That ripple is what we call a tsunami. And they can get quite large. On December 26, 2004, I was sitting in my living room playing with my new Christmas toys, right? Let's see, 2004, I was 11. I had my new Christmas toys, playing with my brothers and my sisters. My mom was watching the news, and then the first report of this earthquake in Indonesia came up. 9.4, if I remember correctly. Pictures, videos of this tsunami and of the total devastation. My dad gets a phone call. My dad was in the military. He was in the Navy. Dad gets a phone call. He goes in the other room, comes back 5 minutes later and says, hey, I need to pack my bags. They're sending me to Indonesia. He was gone for 6 months, helping them recover from the disaster of that tsunami. Boy, the stories he came back with. But I want to show you a video of this tsunami. This was a 33-foot high tsunami. Okay? These people are standing on the third story of their building. Some buildings weren't. There are other videos that you can see of people recording it, and they see people on another building over there, and then that building gets carried away, and those people are just gone.
So I think that's their building.
These people? Yeah.
Grab a life jacket.
That's a 33-foot tsunami sweeping its way inland. Now, yeah,
So people died in there, right?
hundreds of thousands. We're still figuring out to this day, 21 years later, how many people died in this tsunami.
So there's very few that survived.
Let me put it this way. There are hundreds of islands in the nation of Indonesia. They're all islands. How many of those islands do you think are 33 feet above sea level? Some of them, definitely not all of them. What happens when a 33-foot wave runs into an island that is below 33 feet? The entire island is swept away. There were islands that had hundreds of people living on them, entire communities. My dad flew to them on a helicopter to see if they needed help, and there was never even a single trace that humanity had ever been there. There were islands where more people died than survived, and the survivors, all they could do was pile the bodies up just outside of town. There wasn't enough people surviving to bury them. They would just let the animals eat them. There was no way around it.
So there's some bodies that probably have never been discovered.
Think about, because when the water comes in, after the energy is dissipated, it leaves again. So we only know about the hundreds of thousands of people that died that we can confirm. We're still figuring out how many people were carried out to sea. Yeah.
Did you just wear a life jacket, aren't you fine?
Huh?
Or didn't you just wear a life jacket?
No. Life jacket wouldn't save you.
From water?
From 33 feet of water. Imagine have you ever been in the ocean and got hit by a wave?
Oh, yeah.
That was probably a 2 or 3 foot wave. 33-foot wave will crush you.
A life jacket don't just like swim all the way back up.
Not if you're crushed. Doesn't matter. If that water holds you under there, if the energy of that wave holds you underwater for longer than you can hold your breath, it doesn't matter if you have a life jacket.
Would it be easier for them to find you if you did?
I mean, yeah, but that doesn't help you much. It's true. It's not at the top of my mind if I'm wanting to survive, though. Right? Yeah. You may. So this was a terrible, terrible disaster, and one of the reasons why we are working so hard to understand earthquakes and their consequences more and forecast them better. Okay? Try and prevent a disaster like this from happening again. Yeah. How do we try and prevent this from happening? Well, we have monitoring stations, seismometers, and other types of monitoring stations set up all around the planet. After the Indonesian earthquake, the amount of seismometers that were installed around the planet tripled, I want to say was the word. It was the statistic. I think it tripled the number that were set up everywhere. So that we can get faster, better, accurate information about when these things are going to happen and where and how bad. Okay? Japan, Alaska, California, those are a few hot zones. Now, the tough thing here, when you're trying to figure out when these are going to happen, is it can be very difficult as a geologist who is in charge of sounding the alarm. Because if you sound the alarm, hey, this is going to happen, the city responds. They say, all right, evacuate the people, shut down the businesses, let's get people out. If an earthquake doesn't happen, you're cooked. Yeah. They usually fire you because the city or the state or the nation has lost probably millions of dollars in revenue from the amount of time that they had to get people out and how much it costs to do so and all of that. Okay? And not to mention lost tourism, right? If you were in a tourism area, you lose a lot of money. It costs a lot of money to get that machine back up and running. So you are probably cooked. And so it's very tempting as a scientist to say, I'm going to wait until I'm absolutely certain. But that's dangerous too. Because what if you wait too long? And that's exactly what happened in Italy in 2009. There was an earthquake. And it turned out that the scientists, the geologists in charge of monitoring for this sort of thing, knew that there was going to be an earthquake, but they kept it close to the chest until they were absolutely certain. But by the time they were absolutely certain, the earthquake happened and people died. And they're in prison to this day. Oh, yeah. It was their job to sound the alarm, and they didn't. That's manslaughter. Yeah. People died. I don't remember exactly how many, but people died. So, it's important that the information is accurate, but also reliable. And that's what we're working on as kind of a collective group of earth scientists, okay? In the long term, it's always safe to remember that earthquakes do come back. Why? Just because that energy is released does not mean that it's not building up again in the first place, right? The same force that caused that energy to happen in the first place is still there. You can also get a daisy chain effect from these things, by the way. One little earthquake here can actually cause another earthquake a little distance away. So it may go boom, 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 up a fault line. That's absolutely possible. It's known to happen. If you see one earthquake over here, sound the alarm further up the fault system because it may daisy chain its way up there. Okay? You know what would be cool? If we used Twitter for something useful. Oh, yeah. Think about how quickly news is shared on Twitter. I get more information faster about stupid Kardashian news that I don't care about than I get those emails about earthquakes. If we used Twitter for something useful like, hey, an earthquake just happened here, I would hear about it way faster. But, oh yeah? Elon loyalist, I see. I'm just kidding. Yes, sure. Okay, so how do we use these waves to understand things under the surface? I taught you weeks ago that the core is solid, the outer core is liquid, the mantle is solid, all that stuff. How do we know? It's mostly because of how we utilize these earthquake waves. We know what type of waves will go through liquids and what type will not. So we pass these things underground. Some waves will reflect, refract, or diffract off of different materials and states of matter. Okay? Reflection is when something just simply bounces off of another surface. Okay? Like light off a mirror is reflected. Then you've got refraction. Careful. Okay? Then you've got refraction, which is when light is offset, I guess you could say, in different mediums. Yes? Sure, yeah. An example of this is, have you guys ever had like a glass cup with water and a straw in it, and you look at it on the side, and the straw above the water and the straw under the water are offset from each other? Okay, that is refraction of light. You are seeing the same image of that same straw, but under the water, that light from the sun is refracting the image of that straw to be offset from the actual straw above the water. Okay? Same reason why when you're going spearfishing and you think the fish is there, this may not actually be relevant for so many of you. But take my word for it, when you're spearfishing and you think that the fish is right there and you stab at it, you're actually a couple inches off because the light is refracted. Huh? Yeah, it's a little bit different away. It's a little further away than you think. Huh? Just use a fishing net? Exactly. Well, that's the easier way. That's the easy way out. Boo. That's the noob way. All right. Then you've got diffraction. Diffraction is when your wave encounters a new surface and then travels along the outer edge of that surface until it can return along its original path. So using those three interactions of seismic waves with materials under the Earth's surface, we have been able to come up with a reasonable explanation for what the interior of our planet looks like. Yes? Solid inner core, liquid outer core, solid mantle. That's what our planet looks like on the inside.
If our planet got split in half and I saw that exact picture, I'd be kind of bummed.
You'd also be dead.
Yeah, but I mean, like if I was in space and the planet
if there was a force powerful enough to split our planet in space like that, if you were close enough to see it, you'd probably still be dead.
Oh, that's
Yeah.
nice. Yeah, if the light wouldn't really, or if the Earth got split and we were on the other side.
No. No, no, no.
So what would happen in that instance? We would all die. But like, would the Earth cool off really fast? Or
Why is the Earth a sphere? Gravity has formed it into a sphere, but also the forces of our spin and such. We are spinning along an axis while we are circling around the sun at 100,000 miles an hour. You split our sphere in half, it is no longer a sphere. What happens to the two halves? They're going to get ripped apart by the tidal forces from the sun. We become an asteroid belt pretty quick. Yeah. A sphere is the only safe shape that exists for us on our planet.
Can't be a square.
No, we cannot be a square. But also, yes, all the hot components of our planet would cool off in space eventually. It would take a while, but it would. Our planet would no longer be livable very, very, very quickly. Our atmosphere would quickly disperse into space. Our water would freeze and then flash vaporize in space as our atmosphere leaves.
so how long would that be? Like to the split second it gets
For Earth to become uninhabitable almost instantaneously, I would guess, as Earth splits apart and the two halves move away from each other. Yeah, it would be pretty instantaneous. Huh? If they reconnected, I can't even begin to try and understand the physics behind if our planet split in half and then came back together. That would suck.
And he pulls them back together.
Yeah. Oh yeah. He's gonna go Spider-Man. Right. He's gonna do the Spider-Man thing with the fairy. Yeah. All right. Let's move on. Let's talk about plate tectonics. For the longest time, yes. For the longest time, people believed in what is called continental drift theory, which essentially is that Earth's continents are basically bumper boats on the surface of our planet on an ocean of magma, just kind of riding around, bumping into each other. Every now and then they'll come together and make, hey, you want to make a supercontinent? And then they'll come over here, just like bumping around with each other. Yeah.
So if I drill down far enough, magma will come out.
No, that's what they used to think. But now we know better. We know that the mantle upon which the continental plates sit, it's all solid. We aren't bumper boats on an ocean of magma. We know now, ever since the 60s, about tectonic plate, the plate tectonic theory, okay? Which is that Earth's entire surface is solid, but it's got cracks in it, and we are getting pushed and pulled and shoved this way and that way by forces of convection in the solid mantle underneath of us. Okay? We've known that since 1968, but somehow the continental drift bumper boat theory still gets taught in a lot of schools. Okay? Yeah, so what is one way that we know about this? Well, we can see that our plates have come together for a while and then separated again, reinforcing the plate tectonic theory. How do we know about that? Because there are fossils present on multiple continents. Mesosaurus, South America and Africa.
Is that like a bigger version of an alligator?
No, so this is a swimming reptile. No, that's a mosasaur. This is a mesosaur. Okay. Lystrosaurus came before dinosaurs. Cute little dude. Think like it looks like a vampire and a pig, right? Gigantic front teeth like that, but more or less looks like a reptile pig. These were herbivores. Don't let the big front teeth fool you.
Black pig, the brown pig.
Huh? It eats plants. Yeah, it's an herbivore. Those big teeth were for digging in the ground and pulling up roots and stuff. Okay? They are present on most of our continents. Okay? They were all over the place. This is all evidence that at one point all our continents were together and split apart. And came back together and split apart again, and came back together and split apart again, reinforcing the plate tectonic theory. Okay? We're not just bumper boats. They're plate tectonics, and it's much deeper.
Like everyone before 1968 believed the bumper boat theory.
Matter of fact, I still have a whole bunch of paper teaching material from the guys that taught geology at Odessa College before I came in that has continental drift theory as the material that was being taught.
What year were you born?
Do the math.
I don't know.
All right, how old do you think I am? I think we've covered this.
32.
I'm 31.
Oh, I was close.
1993. Yep. Okay. So this is convection. This is the convection that is causing plate tectonics. Okay. So we have convection cells in the lower mantle, which feed convection cells in the upper mantle, which cause the movement along our crust. The pushing together, the pulling apart. Where you have two convection cells going in opposite directions, they pull the plates above them apart. You have convection cells going towards each other. You have tectonic plates that run into each other. Okay? So because we know how these mechanics work, we can make some fairly accurate, we think, approximations for where the tectonics will be in the future. So in about 50 million years, this is what our Earth should look like, assuming that all of the convection cells keep going where they are now and all of the plates continue moving in the same direction they are now. No. Where's the Mediterranean Sea? It's gone. There's no Mediterranean. Europe and Africa have come together and made a new continent. I don't know, what would we call this? Eurafrica?
Yeah.
But what about Asia? Wow. Live on YouTube. Canceled. All right. What's next? Eurafrasia? 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 Eurafrasia. Yeah. Okay, we'll call it Eurafrasia. It's been decided, YouTube, we're going to name this Eurafrasia. No takebacks. Trademark Joshua Hart 2025. All right. South America, the Panama Canal is gone. Panama itself is just gone. So there's a little inlet between the Atlantic and the Pacific again. Very nice. Okay. Antarctica, still hanging out there. Australia, moved even further north. Okay. It's now sitting on the equator. Might be a very nice rainforest there for all we know. Okay. 250 million years in the future, we're looking at something like this, theoretically. Everything has come back together and formed a new supercontinent called Neo-Pangea. I really hope no one got paid to come up with that name, because that's such a cop-out.
So what if like Antarctica came in?
What about Antarctica? Where is Antarctica here? It's at the bottom in 50 million years. It's at the bottom in 250 million years. Well, that's lame. Are we just leaving Antarctica out on purpose? Are they that poor friend that we used to socialize with, but now whenever we have a party, they just stand sadly at the window and look at us?
I don't think we're gonna tow out there. I don't think we tow the other one.
No, we can't tow it. No bumper boats, remember?
Because we're in an ice age, that's why it's at the bottom.
No. Antarctica went to the southern hemisphere about 50-something million years ago is when it finally finished settling down there, and it has been there ever since. As far as we can tell, there are no convection cells underneath of Antarctica. It might have something to do with the southern pole, actually. The way that the Earth is spinning, the convection cells in the mantle may not actually be active in the southern pole, which means that Antarctica, as far as we can tell, will stay there forever. There's no reason to think it'll move because it's not moving at all right now. So we can't model it going anywhere. Yeah. That's not what I said.
Like if I was alive, 250
I mean,
years.
yeah, I mean, think about, here, let me go back a slide or two. Look at this. Do you know where this is? South America. You know where that is? Africa. That's Arabia. That's India. This is, this is Australia, okay? You know what that is? No, that's Antarctica. Antarctica was part of Pangaea with everything else. But after Pangaea broke up, it went south and everyone else went north. And it has remained in the south to this day. All right, so the last thing I want to mention is magnetism in rocks. I taught you that Earth has a magnetic field, right? That magnetic field generated by the interaction between our solid and liquid cores is generating, it's making that magnetic field, which is protecting us from most of the solar radiation. Have you guys ever seen the Aurora Borealis or a picture of it? Okay, that is ionized radiation coming into our atmosphere at the poles, North and South Pole. It happens at both places, okay? It's funneled there by our magnetic pole. It's kept from hitting us dead on by our magnetic field. Yeah, you have a question?
Is it like in the Polar Express, like that?
Exactly, yeah, they show it in the Polar Express. Okay? So it's funneled there and kept from hitting us dead on. It would kill everything on our planet if it did. This magnetic field is keeping us alive. There's some weird and wacky stuff that our magnetic field does, though. Okay? Our magnetic field, being a magnetic field, has poles. Magnetic poles. Magnetic north, magnetic south, we call it. Okay? Right now, what we consider to be magnetic north is in the northern hemisphere. And the magnetic south is in the southern hemisphere. But get this, that's not always the case. We have found rocks at the bottom of the ocean that oriented themselves, they're magnetic rocks, right? They've got iron in them. The iron minerals oriented themselves towards magnetic north at that time that they were formed in the ocean crust. But what they are pointed at is not our current magnetic north. How interesting. So when you go and you take samples from the bottom of the ocean, you'll actually see that there are strips of rock that were made at a divergent plate boundary from when magnetic north was in the north, and then another time from when magnetic north was in the south. And it goes back and forth and back and forth and back and forth. We call these magnetic polar switches, okay, or reverses. When it's at reverse polarity, magnetic north is in the south pole. Okay, so there's a difference here between geographic north and magnetic north. Right now, for you and me, they're the same. For the whole time that you and I have cared about magnets, for the whole time that our civilization has cared about magnets, magnetic north has been in the North Pole. It's not going to be for much longer, possibly, though. It's wandering. When I was a kid, magnetic North Pole was somewhere in the middle of Canada.
So it's changed?
It's now in northern Russia.
They moved a lot.
Our magnetic poles are wandering. And by looking at the geologic record and seeing the history of them switching, we can reasonably assume that at some point, this wandering is going to turn into a reverse.
Is it beyond the equator too? Like that?
It's going to snap from north to south like this, and all of a sudden, magnetic north will be towards Antarctica. And we will be living in the magnetic southern half of the planet.
So we won't feel any different?
We won't feel any different. But our magnetic field is going to be a little wonky for a while, which means more solar radiation is going to make it through. This is never bad enough to cause an extinction. It may impact quite a few animals, though. Birds, bats, whales, they all navigate to their migration on their migration pathways into their nursery grounds using magnetic poles. They might be confused for a while. Is it going to impact our technology? Maybe. We don't know for sure. It might impact satellites, right? It might impact GPS until we can compensate for it. There's no way to really know what the effect will be until it happens. There was a question over here. Yeah.
So like the North Pole and the South Pole basically, South Pole and North Pole.
Magnetic north and south.
I was gonna say, don't we have to call it North America, South America, South America, North America?
No, because that's based on geographic north and south, which is different.
So how is it just gonna switch? It like flips inside the Earth?
It's not so much a change within the Earth. Well, actually, it might be. We're not sure. We're still figuring it out. All we know is that it does it often. And right now, our poles are moving. So we might be going towards a magnetic switch right now.
How long would that be, do you think?
No way to know. No way to know. This is what our magnetic fields look like. They're emanated out this way. So basically, magnetic north, magnetic south are going to switch like this. The poles are going to flip at some point. Don't know when. Any questions about today? I still have to teach you about Lab 5, but I'm just asking if there's any questions about this lecture. Yeah?
With magnetism, it's like it goes around, right?
Around the whole planet? Yeah, its stronger reflective ability is around the middle, and less at the poles, which is why we get the aurora borealis at both poles, because that's where that ionized radiation is getting funneled in.
And then it goes into, right? Like,
Yeah, yeah. Okay. Okay. Any other questions while I pull up Lab 5? All right. Lab 5. I'm going to see if I can get this to you in 15 minutes or less, so you have plenty of time to work on it, okay? Maps, maps, maps. We love maps in geology. What, you don't like maps? Do you use GPS for everything? Actually, I listened to a podcast episode last week while I was working out that said that there is evidence, they've collected so much evidence that suggests that the more you use GPS, the dumber you are at reading maps yourself.
Mom makes me, like whenever we go on a trip, she makes me drive and she gets one of those big maps and she makes me mark my.
That's good. That's good.
All the way to Corpus Christi with a big old map.
Good. That's good. That's good practice. Because like I was saying, we now have enough data that says if you just rely on a GPS, it is that much harder for you to rely on street signs and landmarks. It's actually more cognitively difficult for you to use those. Yeah. When I'm going to a new place, I'll usually go the first time with the GPS, but I'm going to pay attention to the route. And then I test myself by not using the GPS every time after that until I know it by heart.
But that's just a machine, yeah. So you can't really learn like if it's just telling you because it's just giving you where it's at.
Right, exactly. Same principle as AI, my friends, right? If you just ask a question to AI and then it gives you the answer, you are not learning, and therefore you are going to fail at that subject when it comes time to use something without AI, right? That's how it works. All right, so we have many different types of maps here, okay? You've got satellite imagery that we can use as maps. This is a topographic map, which you're going to have lots of fun with today. And then this is a geologic map. Geologic maps, we learn a little bit more about in 1404, but every color on this map corresponds to a different type of rock from a different age. Okay, so there are lots of different types of maps we can use. This is a topographic map of where we live. Okay, here is Odessa, there is Midland. It shows all of the streets and all of that, but notice there are these curvy, wiggly lines. Okay? Hmm?
That's like right, almost right there.
Oh, this point? Not intentional. It's been on this has been on the slide for about 3 years, so I'm not stalking you, all right? I promise. Okay, so these wiggly lines here represent changes in elevation. We call those contour intervals, okay? So they represent a change in elevation. So let's see, let's find one. This one, for example, says 3,000. Everywhere along this wiggly line is 3,000 feet above sea level. Where's the next line? Right here. Let's see, what does this say? Where's the number on this one? That one doesn't have a number. So let's go. I'm trying to find another wiggly line with a number. I think that says, what does that say? Right there. It's so hard to tell on that. I think that's 2,900. Oh, there's 2,900. Okay, this says 2,900 right here, okay? 2,900. This one is 3,000. So between this wiggly line and that wiggly line, we lost 100 feet of elevation. That's what those wiggly lines represent. This is a way of expressing a three-dimensional thing like elevation on a two-dimensional surface like a map. Okay? So that's how this works. This is Earthquake Lake, Montana. This was the result of a landslide that came after an earthquake, a 7.5 earthquake in 1959. Okay? Collapsed this whole side of the valley down into the valley, blocked off this river. The Army Corps of Engineers actually had to come and blast a path for this river to flow out from through the landslide because the river was backing all the way up the valley and flooding out towns on its way up the valley. Okay? So they had to come and blast this out to give the water somewhere to go. This is a contour map of that valley. So you can look how close all of these contour lines are. Let me ask you this. General question of the class. If a contour line represents a change in elevation, what does contour lines really close together mean? I'm looking for something even more basic than that. Exactly. It's a steep slope. Because if each contour line is a change in elevation, the closer they are together, the faster the change is happening over distance, right? Steep slope, very close contour lines. Far apart contour lines, shallow slope. Okay? So you can see how steep the slopes are here along the side of this, and then look at down here how far apart they are. That's the bottom of the valley right there. Okay? All right, so for your exercise, you are going to be using topographic maps to find elevations, but you're also going to be using grid systems to find locations. Okay? Coordinates are an example. Latitudes and longitudes, none of you know how to read those, but you're familiar with them in concept, right? That is a type of a grid system. You are going to be learning about two different grid systems today and using them both on the lab. First one is township and range. Second one is universal transverse Mercator. So let's start with township and range. Yes, go for it. This dot, that's where my car keys are. Someone tell me where my car keys are.
They're in your drawer in your office.
They're right there on the board.
They're right there on the board. Not helpful. Within the bounds of this area that I have prescribed on this
Oh, they're more likely at the front of the room with you.
At the door.
You think that's the classroom? That's not the classroom.
It could be anywhere.
It's just a box. It could be anywhere. Somebody tell me where my car keys are. Anywhere in the world doesn't help.
They're in your pocket.
Nope. That dot is my car keys. Tell me where they are.
In your office.
In your car.
No, this dot is my car keys. Where are they?
It's on the dot.
It's on the board.
But where? Within the bounds of the square.
In the
Bottom right? Is that what you said? Bottom left? Okay, so it's in the bottom left of the box. That's all you can tell me. But how big is this box? We don't know. There's no sense of scale. All you can tell me is it's somewhere in the bottom left of the box. But that covers a whole big area. We need a way to express the location of an object in a given area. That is where grid systems come in. Okay? So if I overlay this with a grid system, we call this township and range in this example. Okay? Townships being my rows, ranges being my columns, works very similar to an Excel spreadsheet where you have your letters on the top and your numbers on the side. If I said box J11, you would know, go to column J, row 11, whatever's in there is what I'm talking about, right? Same thing. That's a grid system. This is a grid system. Now tell me, where are my keys?
in R3. Oh, and 3W.
Okay. You've identified the next factor here. Direction.
Or is that 2S? I don't know.
Yeah. Townships are rows. Okay? They go north and south. Ranges are columns. They go east and west. Why? Why do the rows go north and south and the ranges go east and west? Because we have to have a 0 to start from. If you don't have a 0 to start from, you don't have any frame of reference. So for our ranges, we have what is called a baseline. That line represents 0. Anything above my baseline is north. Anything below my baseline is south. Then we've got the principal meridian. That's the 0 line for our ranges. Anything to the left of our principal meridian is west. Anything to the right of the principal meridian is east. Okay? So with that information, tell me where my keys are.
You're at 3 west, 2 south.
Okay, township 2 south, range 3 west. Good. We've narrowed it down. Problem is, each township and range is 6 miles to a side. I know, we're still looking at a 36 square mile area. I really don't want to look for my keys. I really don't want to look for my keys in a 36 mile area, right? That's unreasonable. Be more specific. Tell me where they are.
Lower left of row 3 west, township 2 south.
That could mean anything. We need to zoom in. We're going to zoom in. The next box I show you is range 3 west, township 2 south. Just this box, okay? This is just that one box. This whole thing is range 3 west, township 2 south. How many smaller boxes do I have? 36. And what was the square area for this? 36. Each one of these is 1 mile to a side. Somebody tell me, these are sections by the way, what section are my car keys in? Okay, we've narrowed it down to a 1 mile square area. That's a little more doable, but still a lot of work. It's a lot of walking. What are we going to do? We're going to zoom in again. We're going to zoom in on section 30. Okay, so here we have section 30 and we're dividing it in quarters. Boom, boom. Northwest, northeast, southeast, southwest. And then we're going to divide those in quarters again. So we have northwest quarter, southwest quarter, northwest quarter, southeast quarter, okay, or southwest quarter, okay, northeast, southwest, southeast, southwest, southwest, southwest. Okay? It's a quarter of a quarter. So this is a half-mile area. This is a quarter-mile area. This is much more searchable for my car keys. This is how we use township and range. Okay? This is relevant because if you ever buy land or own a business, it's going to be the amount of land that is divided to you that you purchase is going to be dictated using township and range format. That's how cities and states and federal agencies keep track of who owns what land is using township and range format. Okay? So, my car keys are in the southwest quarter of section 30, township 2 south, range 3 west. That's how we would say it in township and range format. Right?
I think it was that low.
Super easy.
Is that one of the answer choices?
No.
Is that what they look like though?
Yeah. You're going to be using this on your assignment. Now, here's the good news. Here's the good news. You only have to give me township and range. You don't have to give me the section or the quarter. Okay?
So we just have to give you what that is right there.
Yeah, you're just going to use township and ranges for the points that I give you on this document. You'll find out. It's the first part of the lab. Okay. Now let's talk about Universal Transverse Mercator, UTM format. It's another grid system just like township and range, just with slightly longer numbers because we're not dealing with arbitrary township and ranges. We're dealing with meters, okay? Meters from 0. So we have divided the Earth into sections based upon distance from a 0 line. When you look at one of these maps, you're going to see that along the top and the side are numbers that look like this. This says 61,000 meters east. This one's not there, but that's because there's other text there. This one says 63, 64, 65, 66. Yeah, I mean, further along there would be 67. 61,000 meters east of everywhere along this line is east of our 0. 62,000 meters east, 63,000 meters east, 64,000 meters east. We are gradually getting further to the east away from our 0 line, is what that means. Now for our rows, this is taken from along the side of the map. Look, 68,000 meters north, 67,000, 66,000 north of our 0 line, which is to the south. So if I were to ask you to give me a location for something, using UTM format, you give me two numbers. You give me the row and the column, just like with township and range, just like with an Excel spreadsheet. Okay? I'll show you an example in a minute. But these maps also contain contour intervals. Let's read contour intervals for a minute. Contours, remember, represent what? Changes in elevation. Okay? They represent changes in elevation. Okay? So, which is relation to sea level, by the way. Okay? Elevation is relation to sea level. That does not mean it is always above sea level. Sea level is what in elevation? 0. Do numbers below 0 exist? Negative values. Is there elevation below sea level? Yes. There are parts of the ocean below sea level, right? Remember that when it comes time to do this assignment, okay? So, you've got your contours, and you can always tell what your contour values are by looking for these numbers. This says 8,000. This says 9,000. This says 8,200, okay? This says 7,700. You can always tell how much each contour is worth by either looking at the bottom of the map, where there will be a key that tells you, or by doing the math. How much, let's see, there's 1, 2, 3, 4, 5 big spaces between 9,000 and 8,000. How much is each big space worth? There's 1,000 feet of difference between here and here.
500. I mean, 250.
200. You divide the 1,000 differences. No, it's 1,000 divided by 5. Each one of these larger, bolder lines is worth a 200-foot difference. But there are 5 lines between the bigger lines. How much is each of those worth? 40. 40, 80, 120, 160, 200. So that's a simple way to do that math, okay? Or you can just look at the bottom of the map and it will tell you what the contour intervals are worth, okay? When you are looking at, on these maps, this is important. When you are looking at these maps, elevation is going to be in feet on land. But because oceans are international, they are going to be in meters. On the assignment, I give you a conversion between feet and meters. Okay, so when it's appropriate, you will need to convert for that. We've already kind of talked about this. That's a 200 difference. These two boxes are the same size. This one has 19 contour intervals in it. This one has 9. Which one is steeper? The one with the most contours over the same distance. Exactly. You're good. Catching on. When you are looking at the contours and you see these weird V shapes, those are bodies of water. Those are streams or rivers cutting through your rock, artificially changing the elevation in that local area. It's changing the elevation to be lesser in the direction that the water is coming from. So the V's are always pointing in the direction that the water is coming from on your contours. It's considered the easiest lab, yes. If you pay attention and you do it right. It's really easy to not pay attention and get the whole thing wrong. Okay? All right, so here's an example. What location using UTM coordinates does Dead Man Creek start? Well, first of all, we need to figure out where the heck Dead Man Creek is. Oh, look, it says it right there, Dead Man Creek. How about that? Okay, so now we're going to follow the direction that Dead Man Creek comes from. How do I know? Follow the V's. V, 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 V. Oh, there's no more V's that way. This must be where Dead Man Creek starts in this general area. Okay? What UTM coordinate do I give? This box is the UTM coordinate for where Dead Man Creek starts. Give me a row, give me a column. What am I looking at? Well, this is 68,000 meters north, that line. This line is 67,000 meters north, which means that up here must be 69,000 meters north. So this is in row 68,000 meters north. Why? Because everywhere along this place is going to be 68,000 and something meters until I reach that point, at which point it becomes 69,000 meters. So it's in row 68,000 meters north. Which column is it in? Well, here's 61,000 meters east, 62, 63. It's in column 62,000 meters east. Okay? Those are the two numbers you would give me to answer this question. Okay? You following along? Great. So these are the maps that you will be given. You have Monterey, California. You have Hoquiam, Washington. I have physical copies of these for you guys to work on here in the classroom, but I've given HD, like 4K, very high quality scans of these to you in the lab folder for this lab for my online students. When you download those, and you have to download those, you can't just view them in Blackboard. You won't get the resolution you need. It may take a minute to download them because they are 4K. You can zoom in very far on these things and they will be crystal clear. But it takes a minute to download them for you to get that kind of quality. Not necessarily. How good are your eyes? Okay, then your eyes will see better. All right. So, any questions about this lab before we get started? All right, then I'm going to end the recording here and hand out the labs.